Okay. Okay, so our speaker today is Yiting, and she's going to talk to us about flat tree.
Hello everyone, I'm Yiting. I'm a 6-year PhD student working with Professor Yiting in the Bob lab. And today I will talk about my research about flat tree, which is an unconventional and might be crazy design of data center network architecture. So most of today's talk will be like a tutorial. So instead of giving you a whole lot of computations about my research, I will spend most of the time showing them very basic backgrounds about data center networks. So I hope after today's talk, you will get the basic idea of data center networks and get a very high level intuition of my research. Okay, so let me start from cloud computing. It has been a very hot topic for almost like over a decade in the research and industry. Okay, so the gist of cloud computing is to build a ubiquitous shared platform of computing resources. So users can access these computing services at any time, anywhere, with any device. And there are a lot of services provided by the cloud. Okay, so let me ask a question first. Please raise your hand if you think you are an active user of cloud services. Okay, good, almost all of you. So if you use Google, you use Google's cloud service. Like you just send a request and there are very complicated processings going on in the backend in Google's cloud, and it gives you back the result. Okay? And if you go to Facebook, you are using Facebook's cloud service. And many of you have used Amazon EC2, like you can rent some virtual cluster resources on the public cloud provided by Amazon. You don't need to go buy your hardware or set up your own cluster, right? Or many of you are using these big data computing platforms such as Hadoop and Spark to run machine learning jobs. So for any of these, they are all cloud computing services. Okay, so we see the magic of cloud. It's like some fluid computing resources floating in the midair. Okay, so how does it really happen? So what supports the cloud services? Data center. So what is a data center? Here is a picture of a data center. It has a very large warehouse of numerous number of machines. These machines are organized as clusters and connected together using a computer network. Okay? And network plays a very important role here in data center network because we have many computing nodes. And the computing is local on each node, and it has local memory. But they need to use the network to talk to each other, to exchange the data, like intermediate computing results, and also they need to access the outside world. So network becomes a bottleneck of the performance for cloud services. Okay. So how to build a very efficient and powerful network for data center? We need to study the network topology. Okay, what is the network topology? So in data center networks, there are two types of nodes: servers and switches. So servers are like the end nodes where you put your computation on, and they are connected to these switches. The switches are connected to each other as joint points in the network. And they only, and the edges so you can see a network topology as a graph. So these servers and switches are all nodes in the graph, and the edges are the links that connect them. Those are physical cables, like optical cables with super high bandwidth to connect up these nodes. Okay? So network topology defines the way to arrange these elements, how you connect them up. So if you have some basic understanding of graph, different graphs have different features, right? Different properties. So say you are going to build a network, and you have the fixed amount of money. So you can decide how many devices you want to buy, right? You can determine like the number of switches, the switch port count, and the number of servers. But how do you, like, given these fixed number of nodes, and also the number of edges, those are the cables you buy from the market, how do you connect them up to have the highest performance? That is the question. And we can see there are many different kinds of topologies to wire up the network. Okay. So what is a data center topology look like in today's data centers? It is called Clos network. So the Clos network, especially three-stage folded Clos, is the standard data center network architecture in today's data center. So Google's data center looks like this. Facebook's data center looks like this. Amazon's data center looks like this. Microsoft's data center looks like this. All data centers, almost all data centers nowadays look like this. Okay? So it is called Clos topology. It is named after a very famous network researcher, Charles Clos. So the right pronunciation is Clos, not Clos. The S is silent. So every time I hear people say a Clos network, I was like, ooh. So it's very much like when you hear people say Illinois or Arkansas, or even call the German musician Bach as Batch. So go to look up the pronunciation before you pronounce a foreign word, okay? Otherwise, you will just embarrass yourself. So the right pronunciation is Clos. Okay? So a Clos network looks like this. The switches are divided into three layers: core switches, aggregation switches, and edge switches. And servers are only attached to the edge switches. They are not connected to aggregation or core switches. Okay? And the edge switches, so Clos network defines this particular type of connection. Locally, the edge switch and aggregation switches are connected to one another in this way, like one at each port. Okay? And then the aggregation switch uses uplink ports to connect to the core switches in this particular fashion. Okay? So just remember how it looks like. So next time, if you want to have an intelligent discussion with a network researcher, throw this jargon to them. Say a Clos network, okay? And when your friends are even at the level like, say, come look at my cool app on my phone, you tell them your app is running on a Clos network. It's even cooler, right? So why are all data centers using this Clos topology? Because it's very easy to build up. Why? So in practice, people package some devices into a large container called pod. Say, let's go back to this picture of a data center. You see, there are a whole lot of machines here. So if you just wire them up randomly, it will be very messy, right? So people need to find ways to aggregate the to bundle up each single wire and to wire them up very neatly. So instead of wiring the devices up one by one, people decide to use this container called pods. They just put these devices into the pod, and these connections are hidden internally into each pod. So this is what a pod looks like. It's just a big box. And if you look at the inside, there are just the servers, switches, and the wiring, cooling, everything packaged together. So you, like a driver, drive a 18-wheel truck with this pod as the load, and they drive to the data center, and people put together tens of these pods. Okay, so they don't need to care about what's internal in these pods. And the pod only exposes to the outside world some external connectors. And these are super big connectors, like not individual wires, but multi-links. So you can just hook up these super connectors and all wiring them. So in this example, you just have 4 pods, and they are each functional individually. And you just connect them up to this another layer of core switches, and you have a data center. Okay, it's very neat. Okay, people like this kind of topology because it's implementation friendly. And as I have shown, you can use path. And also the wiring is central. Like one of the reasons you can use path to ease the implementation is all wiring is central. Because every pod looks exactly the same. Like you can manufacture the same kind of pod and just duplicate it. Okay? But say, and also because the wiring is central, you just need to connect this pod to this central layer of core switches. So imagine a data center warehouse. You just put together these pods, and all the uplink wires go to the same place. And when something goes down, it's very easy to trace them. Okay. But the problem here is the performance is suboptimal. So this is another view of the Clos topology. You see, if I want to send traffic from the edge to someone else on the edge layer, I must go through multi-layers in this tree. So the hop count is very long. So that's a waste of network bandwidth. If I connect these two nodes together, then I can use the bandwidth more efficiently with only one hop, right? And because Clos is a very flexible topology, you can build such a network with different parameters. You can scale it up or down with more number of nodes or less number of nodes, or you can add some more layers. Like in this example, we have 3 layers of switches. We can build like 4 or 5 layers. So in that case, and it's also very flexible because you can have oversubscription. Oversubscription means a switch has less uplink bandwidth than downlink bandwidth. So that, from the perspective of a graph, that means there are a whole lot of bandwidth at the edge, but you get thinner and thinner bandwidth in the core. So the core can be a performance bottleneck. So this is the trade-off. It is easy to implement, but you must pay the price to have suboptimal performance, okay? So another kind of topology that caught us eyes in recent years is called random graph. It has very good performance. So what is a random graph? You still have the same number of switches, servers, the same port count of the switches, but you connect them up randomly. You just randomly connect the switches whenever there are ports available. And this, compared to the Clos topology, which only has the servers connected to the edge switches, here the servers are connected uniformly to all the switches. So there's no hierarchy here, no particular structure. All switches are equal, and they have the same number of servers connected to them. Okay, so if you have some basic understanding of a topology, of a graph, okay, this kind of graph has very short average path length because the nodes are connected very closely to each other. And that transforms to better bandwidth usage in the network. Okay? But the problem is it is very hard and almost impossible to implement because you cannot use a pod. Every node is just different. And you have this neighbor-to-neighbor wiring. What's neighbor-to-neighbor wiring? So in a Clos network, all the wiring is central, as I have shown. But here, every switch needs to be connected to everyone else. Okay? So you cannot just aggregate the wires and put them to the same place. Instead, you must have the very messy connections to have them connected to each other. So it's very much like a mass of spaghetti. And it's very hard to wire up. And even if you wire up, when something goes wrong, it's very hard to have troubleshooting. Okay? So in summary, a Clos network is a tree network. You can view it as a multi-rooted tree. The tree network has good structure, so it's very easy to implement. And Clos topology and random graph is a kind of flat network. There's no structure, and all switches are equal, so it has good performance. Then a natural question to ask is, can we combine the best of both worlds? They seem pretty incompatible. So nowadays, people build fixed network topology, right? You have never heard about a changing network topology. It's like, no matter like internet or data center, you buy this device, you wire them up, and they're there. Okay, you never change the network topology. So it's very hard to combine the best of both worlds using the fixed topology. So let me give you a bit of literature review. Here we put the Clos and random graph into the extremes of the scale of the design space. Okay, so on this side we have easy implementation, and this side we have good performance. And in the past decade, network researchers have proposed many topologies to achieve good trade-offs between these two features, like fat tree, BQ, E-cell, and HyperX. So the basic idea is this. So they don't use the Clos structure. They change the structure. But it's still a structured network. Okay? Structured network can be implemented. But it may not be as easy to implement as a Clos network, but still reasonably easy. Okay? And the graph these architectures, these works proposed, can have better performance than a Clos network. But it's very far from random graph. Okay? So, but still, it's very hard to combine the best of both worlds, because in a data center, you have a lot of cloud services. The traffic can be fluid, right? Like you want this kind of service today, tomorrow you want something else. And you may want to, and there are like emerging services in the future. No one can predict it. So it's very hard to use a fixed topology to service all sorts of applications. Okay? So if fixed topology is the bottleneck, why don't we just change the topology? If we have convertible cars in practice, why can't we have convertible data center networks? And by definition, a convertible data center network is a network that can change its topology. So conventionally, how do people change the topology? You just uncable those wires and wire them up into a different device, so you connect up the network in a different fashion, right? But this is not what we want to do, because it's very painful, requires a lot of human effort. But by our definition, convertibility is you hit a button, and there's some magic software that can change the topology automatically for you. Okay? So I call my a network topology as flat tree, because it combines the good features of a tree network and a flat network. It is as easy to implement as a tree network and has good performance as a flat network. Okay? So here are some design highlights. So flat tree starts from a Clos topology, because we know how to build such a network. Okay? And we convert its topology to approximate random graphs. So what we are doing is not to build a random graph, but to approximate random graph. Because random graph is purely random, we cannot use a structured topology to build a random graph, but we can achieve reasonably good performance to be close to a Clos network, or to be close to a random graph. Okay? But there are challenges, because these two topologies they don't look like each other. So how can we bridge the gap and convert from one to the other? So here are the set of challenges. So first, how do we relocate the servers from edge switches to aggregation switches and core switches? So in a Clos network, servers are only connected to edge switches, right? How can we move them to all the other kinds of switches? How do we move servers? And second, we need to break down the hierarchy of Clos network, flatten the network, and connect core and core switches directly. Okay? And the third, we need neighbor-to-neighbor or peer-wise wiring in a random graph. And as I have shown, the neighbor-to-neighbor wiring is always painful. How can we achieve this with low wiring complexity? And the fourth, random graph has good features because it has optimal performance for uniform traffic. uniform traffic means so the traffic is uniformly split out in the entire network. Okay, but sometimes the traffic can be skewed. Like you have more traffic in one part of the network and the very scarce traffic in the other of the network, right? Can we adjust the topology to give more bandwidth to this intensely communicated part of the network? And the fifth question is, can we combine the different topology? If we have the ability to change the topology, then can we partition the network into different zones with different topology in each of the zone? So we can put different services in each of the zone that aligns well with the kind of topology. And the last is the practical issue of packaging. Can we hide the complexity into a pod? Like we just manufacture a different kind of pod. But from the network operator's point of view, the network has not changed because they only see the external connectors and they can wire up the network in the old fashion. This is what we want to do. Okay? So next, let me show you how we do the magic and change the topology. We use converter switches. So here's an example of a converter switch. Okay? So we have 4 nodes connected to this converter switch. And by changing the internal connectivity, we can achieve different topologies. For example, here, we have A connected to B and C connected to D. C connected to D. Okay? And we can use a configuration software to change the internal connectivity to have A connected to D and B connected to C. And we can also have A to C, B to D. And this type of device is very simple. We can use the off-the-shelf switch on the market, and it's very cheap because first, there are only a few, the port count is very low, only like less than 10 ports. If you have some background about network devices, usually the price of router or switch goes exponentially with the port count. Okay? And the logic is very simple. You just pipe traffic out through different ports. No complicated logic like processing, buffering, nothing like this. So it's very cheap. And because it's very simple, we can see it as a physical layer device. Okay. Now let me show you how can we move the server using this converter switch. Here we have a 4-port converter switch. We have a server, edge switch, aggregation switch, and core switch, all connected to a converter switch. And by this type of configuration, we have the server connected to edge switch, aggregation switch connected to the core switch. We have the flow topology, if you still remember the hierarchy thing. Okay? And we can change the topology to connect the server to the aggregation switch and edge to core switch. So this way, we move the server to the aggregation switch, not at the edge anymore. And we connect edge to core switches directly. Okay? But this, we also need to move the server to the core switches because all switches are equal in the random graph. But we cannot do it by this type of converter switch. Why? If we connect the server to the core switch, there are only 2 remaining ports. We have to connect edge and aggregation switches. And if you still remember the Clos topology, there are abundant edges between the edge and aggregation switches. We already have a lot of this type of wires. If we add more, we don't add capacity to the network. So we introduce another type of converter switch called 6-port converter switch. So the 2 additional ports are side connectors. We can connect 2 converter switches together. So in this way, we can move the servers to the core and connect aggregation to another aggregation switch and edge switch to another edge switch. Okay, and we can also swap this connection to diversify the type of links. Okay, so let me give you a very simple toy example to go through my design. So this is the original Clos network. We have 4 pods. This is the Clos pod. If you remember the picture I've shown you, so the servers are connected to the edge switch, and edge switch connected to the aggregation switch connected to the core switches. Okay? And the trick here, all these things we add to this architecture is we put converter switches into this pod. Okay? And we break down the original links between the aggregation switch and the external connectors. And we also break down the links between servers to edge switches. And we connect them all to the converter switch. Okay? And another change is we change the wiring between the pods and the core switches. And I will talk about it later. And the last change is we connected these pods together. Like we connect each pod to the adjacent pod using the side connectors of a 6-port converter switch. Okay, then let me show you the example. If we use this type of configuration, what we'll achieve. The servers are connected to the edge switch, but all servers only connected to the edge switch. Okay? And aggregation switch is only connected to the core switches. So this is the Clos network by this configuration. So we achieve something like this. And we can also change the configuration. If we use this configuration, we move this server up to this core switch. We move this server to the aggregation switch. And the edge switch is connected to this edge switch in the adjacent pod. And this aggregation switch is connected with this aggregation switch in this pod. So we will achieve something like this. This is very much like a random graph because every edge switch has one server, right? Aggregation switch has one server. Core switch has one server. So the servers are distributed uniformly in the network. And we have more types of links. Instead of just having the hierarchical links only, now we introduce other types of links, like side links between aggregation switches and edge switches. And we also connect the edge switch to the core switch, right? So all types of links, all type of uniform distribution of servers, it's very much like a random graph. Okay. I need to mention here. So why we need to change the wiring pattern between the pods and the core switches? You see some of the links are swapped. If we don't swap these links, say here this server is connected to this core switch now. But if we don't swap this connection, it is connected to this core switch. And if every pod has the same kind of connection, only the first and the last core switches will end up having a lot of servers. And these two core switches will have none. So that's not very uniform. We don't want to do that. So we play with the wiring pattern. We design a reasonably easy wiring pattern that also permutates the server distribution. And we can also form a local random graph. What is a local random graph? It's a smaller random graph within a pod. And these smaller scale random graphs are connected together through the core layer. Okay. And we can achieve this using this type of connection. You can see this server is connected to this edge switch, and this server is connected to the core, the aggregation switches. So it's kind of uniform within the pod. And the edge and the aggregation switches are both connected to the core switches, so they are kind of uniform. Okay? So what we achieve is here, this kind of topology. So why we only connect up pods, why we only connect up adjacent pods? As I have shown, we need neighbor-to-neighbor wiring to approximate a random graph, right? but we don't want to have very messy wiring from every pod to everyone else. So a neat way is to connect up adjacent pods only. And we also use multi-link connectors, as I have said, the huge bundles between the pods. So although we introduce neighbor-to-neighbor wiring, it's not a lot of trouble to the network operators. They can still use a pod, but they just need to connect adjacent pods together. Okay. All right. So here are some details. I'll probably...
Are these physical switches or software controlled?
Yes, those are physical switches, but you can use software to change its configuration. So the effect of changing the configuration is the same as like manually uncable and recable the wires.
So it manually, is it more like the software defined where this is at the physical level and not at the IP level where it's
No,
sort of...
it's at the physical layer, but it's still controlled by software. Okay. So I'll probably just skip all these details, give you only the highlights. So I have introduced the 4-port converter switches and 6-port converter switches. How do we package them in the pod? So we just have these two kinds of blades, blade A and blade B, and we put them on the two sides of the pod. And as I have shown here, the converter switches needs to be connected to the edge and aggregation switch, right? So we just place them on the two sides of the pod and connect them to this set of switches. And we hide the wiring within the pod. Okay? And as we can see, blade A has 4-port converter switches and blade B has 6-port converter switches. And we define the particular way to wire them up. And we change the wiring pattern between the pods and the core switches. Okay? So the wiring is a little bit complicated. I have designed 2 wiring patterns, and they each work well in different scenarios. But the takeaway point is the wiring patterns, compared to the very simple wiring pattern in a cloud network, it is a bit complicated. But it is still doable because it is a repetitive pattern, very regular wiring pattern. So you just need to be a little bit careful to wire up these devices in different ways. Okay. And about server distribution. So how do we distribute the servers to the switches in the network? In my toy example, I have shown you how I can have every switch connected to only one server. So that's very uniform. But in practice, if we have a larger network, how do we distribute it uniformly? So this is a question. And we have designed a way of network profiling. That is to change the parameters of the network. And by each parameter, we calculate the average path length. And we try to get the setting that results in the minimum average path length. So that way, we can determine how to distribute the servers. Okay? And the interpod wiring, that's like how we streamline the wiring between adjacent pods. We need to sort the permutation of the wiring. Like we need to know how each device is connected to some other devices. And we just use a super bundle, and we sort the permutation within the bundle. So you just need to hook them up. You don't need to care what's going on internally. Okay. So here are some summary of the simulations. So the goal is to approximate a random graph. So we did experiments to show it is close in both average path length and throughput. So random graph has very low, very short average path length, right? If you remember, the switches are very closely connected to each other.
How many total nodes are there in this graph? Like how many switches and how many pods?
So actually, I vary the scale of the network. So this is a very high level summary. Yeah. Okay, but the main point is flat tree is only a little bit longer, has only its average path length is only a little bit longer than the random graph. And it improves a closed network significantly. Okay. This is the comparison between the global random graph. That is the random graph for the entire network scale. Okay. And we also construct a pod level local random graphs. And we can see actually flat tree outperforms the counterparts. So the two-level random graph is almost the optimal you can get. You create a random graph within the pod, and you connect them, connect the different pods together. So flat tree even outperforms the two-level random graph because we still use some structured Warren patterns. It is better than pure randomness at small scale. Okay. And we also calculate the throughput. So we use some pervasive traffic patterns, very popular traffic pattern generated in widely used applications in data centers. Okay, so we chose hotspot traffic, which is like one node talking intensively to a lot of nodes. And we also chose small cluster traffic. So it's like a small number of nodes talking intensively to one another. So if you have some background, the small cluster traffic resembles the MapReduce kind of application when the shuffle traffic in MapReduce job. Okay. So for these two types of traffic, we can see flat tree has very close throughput compared to a random graph, and it can improve closed network significantly. Say for the hotspot traffic, it is 1.5 times better than closed network. And for small cluster traffic, it outperforms the optimal solution, in some of the cases, and it's 9% worse in the worst case. And it still improves flow a lot better. Okay. So in conclusion, flat tree converts from a closed network to a random graph. And this conversion is all automatic, controlled by software. It has low cost. As I have shown, we add those converter switches to the network. We need a lot of these devices, but they are very, very cheap. Okay. So flat tree can achieve the easy implementation as a closed network. You just implement it as a similar fashion as a closed network because it hides all the changes, almost all the changes into the pod, and it uses a regular pod core wiring pattern, and we use multi-link connectors between adjacent pods. All these makes it very easy to implement, and we can let flat tree function in hybrid mode. Because it has many pods, we can have every pod configured with a different topology. So when you don't like this type of topology, you can just hit the button and change to some other topology you like. And with the simulations, the result shows the performance is very similar to a random graph. So we did a good job approximating random graphs. It has very similar average path length, and the throughput is only 9% lower in the worst case. Okay, that's all. Thank you.
So I did not follow the experimental comparison. So first, what do you have a constant between the flat tree and random graph? Are the number of nodes and the number of connections same for both?
Yes.
So for both the cases, the
Yes.
number of connections is also the same. So that means that you change the probability of a node being connected differently.
So it's like this. We use the same number of devices, but we just change the way we wire up these devices.
No, but you can, how many basically links do you put? Because you can have a random graph, you can have a complete graph, right? So what is the probability?
Oh, so every node is degree bounded. So we form random graph with a fixed degree. So it's not a complete graph, because that
And
way it will have a lot more capacity, right?
Yeah.
So we have the same number of devices, we have the same number of switches, servers, and each switch has the same number of ports. The number of ports is just the degree.
Also, I would think that the strength of random graph is basically not just the average path length, but the distribution is very concentrated around the mean, right? You can have a small average path length, but then really bad cases where some
Yes.
nodes are.
Yes.
So how does the two distributions compare in case of flat tree and random graph?
So it is a very good question. But so we didn't conduct that kind of experiment. We don't have comparison results for that. But here we chose for the throughput experiments. We chose the two types of traffic. So we want to be realistic. So these traffic really exist in the data center networks. So in the worst case, as you have said, there are some weird traffic, but they almost never exist in a data center. So actually, flat tree is not a random graph because it has a lot of constraints, right? Well, there's just no magic. We cannot just approximate a random graph as a random graph is. But the thing is, if we can approximate random graph, we can show very similar performance for practical traffic. That means we can use this approach in practice, and that's good enough.
So if you went to some manager at Amazon today and said, hey, I have this flat tree, you should build your next data center with it, what would you say would be the biggest obstacle for them for actually implementing this?
Obstacle?
Yes. Like if they said no, what would be the reason they said no?
I think the obstacle is, well, that applies for all kinds of data center network topology research, because you've already invested a whole lot of money into your data center.
I'm
So
saying they're building a new data center.
yes, they need to throw away their device
I'm
and
saying
be
assume they're building a new data center.
a new data center.
Yeah.
Then I would say this is the best solution.
There's no reason to think that they would say no.
Now,
The obstacle might be they really need to go and read the research papers.
So did you actually present,
if you
did you present this algorithm to one of the, like, Amazon, Google, someone, and did you get any feedback from them?
yeah, so actually, I recently just got a paper accepted by Hotnest. You can go read my paper. And Hotnest is the top workshop in networking area. It promotes novel ideas. It doesn't promote like very solid work, like complete experiments. It promotes novel and might be crazy ideas. So, and
Are
I
you
got
suggesting this is crazy?
yeah, and that's why I got it in. And so actually I got 5 reviews, like feedback from 5 reviewers. Wow, it was incredible. Actually, Eugene told me this is the most positive reviews I have ever seen in my entire career. So I'm proud of it. So the thing is, well, it is still debatable, but it might have a lot of impact in the future. It shows possibility of this kind of research. And this is just the first step, one design point. And you can, so previously, almost all the data center networks are fixed. So I have shown possibility. You can change the topology. And this is just one way to change it. You can combine different types of topologies together. And there are a whole lot of research opportunities. Say, if you change the topology, how do you adjust the routing, right? So it's a joint optimization. And some other useful features. Say, here, I changed the topology for better performance, but you can also change the topology for better management. Say, you want to power down half of your data center when the workload is low. So now you need to manually go there and switch them off. But if you use my solution, I just change the topology and have like more bandwidth for part of the network. The other part just gone, they are powered out. Or like when a link is down, I can manually have a backup link. I don't need to go there and change the link manually. So there are a lot of impact. So this is just a very primary step in this topic.
So I have a very practical question. So given the current, like, it's probably closer to what Nick asked, given the current structure of how pods are built, is it possible to convert them into flat trees without really incurring a very
It's
heavy
very
cost?
hard because
So like
you
I
can
would,
see so this is what it looks like now, and we need to add new things. So one neat thing is we package everything in the pod. So when you manufacture a new pod, you just buy a new one. You don't need to care about this change. But if you already have this kind of network, then you need to go to build it yourself. Then it's very complicated.
So basically, you're more targeting the manufacturer, right? Versus like, oh, the user, like Google and Amazon. So you want the next pod manufacturer to use your topology when they're like wired.
So, yes and no. So like all the networking research are more focused on like how you build the network. You need to be friendly to the network operators, okay? But the ultimate goal is to service the users better. Say, if we change from like, this type of topology to this type of topology, that means you can have a lot more bandwidth in the network. That means like when you go to when you have a Google service, the computation is faster. You can have better results. So it will benefit the end users ultimately. Did I answer your question?
Yeah.
How quickly can the topology be changed?
It's pretty fast, actually, on the scale of milliseconds. But because you don't change the topology very often, you just change it like once a day or just a few times in a month or so at this scale. So it doesn't really matter how fast you change.
So can you go to slide number 13?
Number 13?
Yeah.
Okay.
Okay, probably the 11th. So you are showing between the factory, yes, this one. So generally in HPC community, factories are typically used to improve the performance when you have multiple nodes, networking and other things.
You're talking about factory?
Factories.
Yes.
So, and there are other topologies like torus topology and then for other reasons. So I'm just curious to know, I mean, given a topology in your case, how easy to convert to the other topologies like FAT or torus instead of going to the random graphs?
Okay, good question. So actually, fat tree is a special case of a Clos network. So we can build a Clos network. We already can build a fat tree.
Okay, good.
Okay, but fat tree, you are correct that fat tree is an improvement of a Clos network. But it's an improvement because you throw in more devices. That's why it's more powerful. But by my solution, we don't need more devices. We just change the way it's connected up so it can be used more efficiently, so we can save money. So on one hand, we can build fat tree using flat tree. And on the other hand, if we build a random graph, approximate random graph, it can be as powerful as fat tree, but saves a lot of money. Oh.
Sorry, one question. So it's not very clear to me. I didn't get. So when do you exactly change the topology? Like, do you have like some data why you need like to change the topology now to other?
Okay, it's a good question. So I think, well, it depends on the network operator, like how he wants to operate this network. So it's the same question as like what topology you choose when you build your data center, right? So you need to have some maybe statistics about the traffic, about of the applications in your data center. So maybe different data centers have different kind of services, so they generate different types of traffic, and different topologies can serve different traffic better, right? But here, we just give several options. We show you, like, if you need this topology for a particular kind of traffic, we can do it. But it's your own decision to decide, like, first, what topology I want to go with, and the other at what scale. Because I have shown we can have the hybrid mode. We can have a part of the network working in this topology, the other part of the network working as a different topology. So still, it's up to you.
Okay, so as also one following question. So you said like there would be a few milliseconds if you change like the topologies. So have you like talked about when like somebody would like to change the topology, then all the traffic that's happening right now in the network, what you want to do with that?
I think it will be very good future work. But now we don't do online change of topology. And actually in practice we don't need to do that. It's before before your network goes online, you decide the topology and you go with it. And later when you need to change, maybe you just power off the machine, shut down the current traffic and do the change. And it will not be a very frequent change, so no big deal.
I mean, powering off may not be a good solution when you talk about cloud services.
Yes, but I mean, say if you want to power off, maybe like it's not busy hour, say some of the network is already idle, and you can just power it off. So I just don't envision this topology change to be very frequent online. Yeah.
I think let's thank our speaker again.